Okay, so let's apply this to more practical problems. In many industrial applications, they set up their manufacturing process so that the more costly reactant or the reactant that is difficult to remove from the product mixture is the one that gets used up. So there's often very practical considerations in choosing which one is going to be the limiting reactant. We don't have to worry about that, but that's an application to real life. In the laboratory, we're going to measure our amounts of reactants in grams instead of moles. And that's where the grams to moles to moles to grams comes in. And so to find our limiting reactant and our theoretical yields from the initial masses, we need to add two steps. So basically, we're going to learn what we learned, we're going to use what we learned at the beginning of the chapter, converting grams to moles to grams, but we're going to do it twice in each problem. Okay? So let's look at this example. Here we have sodium and chlorine reacting to form sodium chloride. If we have 53.2 grams of sodium and 65.8 grams of chlorine, what are the limiting reactant and theoretical yield? This is very similar to the problem we just finished. So I'm going to take the numbers and write them under the formulas in the equation. 53.2 grams of sodium, 65.8 grams of chlorine, and we're asked for a theoretical yield. It doesn't specifically say grams. Grams is a safe thing to assume. On an exam on mastering chemistry, it's going to give you a unit, and so you'll know for sure. But question mark, grams. We have two masses. We can't assume that they're just both going to get used up. So what we do is we calculate, starting with the amount of sodium, we calculate the mass of sodium chloride that could be made if we had plenty of chlorine. And then we take this amount of chlorine and also calculate the amount of sodium chloride that could be made if we had plenty of sodium. So now we are going to do grams to moles to grams. So 53.2 grams of sodium. I'm going to go from grams of sodium to moles of sodium. And then I'm going to moles of my product, which is sodium chloride. And then I'm going to go to grams of sodium chloride. Grams to moles to grams. The rest of this is just dimensional analysis. I'm going to put the units in so they cancel out. Once you get the hang of it, it's a beautiful thing. So I've got my units working out. Now I need numbers. This mole-mole term is the easiest because I just have to look up here. I don't have to do any calculations. 2 moles of sodium will make 2 moles of sodium chloride. So I'm going to put 2 moles of sodium chloride and 2 moles of sodium because there's a 2 in front of each. Now I need molar masses. So this sodium is an element. All I have to do is look at the periodic table. I don't even have to calculate. I want 1 mole of sodium chloride, and that's going to be 2.99 grams of sodium. I don't want to calculate the mass of 2 moles. The 2 in front of sodium comes in the mole ratio. It does not come in the first term or the last term. So the coefficients from the balanced chemical equation only show up in that middle term. Then over here, grams to moles of sodium chloride. Well, I need the molar mass of sodium chloride. So that's sodium 22.99 plus chlorine 35.45, and it's 58 something. 58.44. So 1 mole of sodium chloride weighs 58.44 grams. Now I just use my calculator. 53.2 divided by 22.99 times 2 divided by 2 times 58.44. This could potentially be a final answer. I'm going to round it. How many significant figures should I have? 3. So it's 135.23 and some other digits. 3 would be 135. So 135 grams of sodium chloride. Any questions? Now I take this one, the other ingredient, the other reactant, and I do the same thing. So I'm going to take the 65.8 grams of chlorine. I'm going to have 3 factors again. They're going to be very similar. I'm going grams to moles to moles to grams. Grams of chlorine to moles of chlorine to moles of my product, sodium chloride, to grams of sodium chloride. And then I put the units in the denominator so they cancel. I want moles of sodium chloride to cancel. I want moles of chlorine to cancel. And I want grams of chlorine to cancel. Again, I like to do that mole ratio first. Sodium chloride, look up here, there's a 2 in front of it. So I put a 2 there. For chlorine, there's no written number. That's an implied 1. The other one that's easy now, because I already figured it out once, notice this last term is exactly the same, right? So I can just copy that down. I don't have to calculate that over again. The mass of sodium chloride has not changed in the last 2 minutes. I need a molar mass up here. This is an element, but it's a diatomic element. The formula here is Cl2, and so then 1 mole of Cl2 is 2 times the mass of 1 mole of Cl. So that's 70.9. So 1 mole of chlorine weighs 70.90 grams. 65.8 divided by 70.9 times 2 times 58.44. $108.47 stuff. Again, this is going to be a 3 significant figure answer, so that would be 108 grams of sodium chloride. Any questions? We're not quite done. We did all the hard stuff, but sometimes on worksheets or on lab reports, a student will have to do a problem like this and they'll stop here. You did all the hard stuff, you have to give me the answers. There's 2 answers requested. The theoretical yield and the limiting reactant. So for the theoretical yield, we choose the smaller. And on my worksheets, if you just put a box or a circle around the smaller one, that's good. I see that you've chosen. And then the limiting reactant is the one that gave us that. So we find the smaller one and then just go back to the beginning of that equation, and that's our limiting reactant. Any questions? This is not the only way to solve these problems. I don't remember for sure. I think your book has you stop at moles and identify the smaller and then continue on. I like this approach because it's more consistent. It's like we're just going to take the same thing we were doing before. We're just going to do it twice. You find the smaller, and that's your answer. So I think it's less confusing. If you have a better way and you consistently get the right answer and can show your work, I'm fine with that. but this is what I'm going to use. Okay, here's another one. Ammonia can be synthesized by this reaction. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? It doesn't mention theoretical yield. It doesn't mention limiting reactant. But I have two masses here. I have a mass of nitrogen and a mass of hydrogen. So I'm going to go to my equation. I'm going to write those down. 25.2 grams of nitrogen. And they're given in an order different than what's in the equation. And 8.42 grams of hydrogen. And then the question, what maximum amount of ammonia in grams? Okay, this is ammonia. You should know that. Question mark, grams. Why does it say maximum? If I take and do this calculation and find this yield, does that guarantee that that's how much I could make from these starting amounts? No, because reactions aren't perfect. Just like making pancakes, you don't always get the number that you thought you should. So again, I'm going to have two calculations, grams to moles to moles to grams. So let's start with 8.42 grams of hydrogen. Grams to moles of product. This time it's ammonia. And then to grams of ammonia. Bring the units down. So I've got moles of ammonia canceling out. And I've got moles of hydrogen down here. Those cancel. And I've got grams of hydrogen. And those cancel. What number should I put in front of moles NH3? 2. Because that's what it says in the equation. If I start with 3 moles of hydrogen, it will make 2 moles of ammonia. So there's 2 moles of ammonia that are created for every 3 moles of hydrogen. Now we need molar masses. Here's H2. I'll squeeze that in up here. 2 times the mass of hydrogen. 2.016. So 1 mole of H2 is 2.016 grams. And then ammonia is nitrogen plus 3 hydrogens, 17 point something, 034, I think. Yeah, that's right, 034. So I take my 8.42, I'm going to divide by, fix up my calculator here first, 8.42 divided by 2.016 times 2 divided by 3 times 17.034 equals 47.429. I'm going to keep 3 significant figures, 47.4 grams of ammonia. Did I do that right? Anybody have a calculator? Yeah, check me because I make mistakes. I saw a thumbs up. Now I'm going to take this mass of nitrogen. It might be tempting to say, well, there's a lot less of the hydrogen. This is going to be the limiting reactant. But that can be very deceptive. I've been teaching chemistry for longer than many of you have been alive. That's a very scary thought. I wouldn't want to guess at this. But apparently this guy wants to sing about it. Maybe I could make him into a YouTube star. You want to sing a little louder? I know the people who watch these on YouTube that don't know what's going on are just like, this person's insane. Well, yes, I am. The authorities just haven't figured that out yet. Okay, so the nitrogen, 25.2 grams of nitrogen. Very same idea here. We're going to moles of nitrogen, and then moles of our product, and then grams of our product. So grams of nitrogen comes down here. I get bored going backwards, so now I'm going to go forwards. Moles of nitrogen down there. Moles of ammonia down here. This term is exactly the same as the one above it. Just going to copy that down. This one in the middle, I just look up here. There's still a 2 in front of NH3, and there's an implied 1 in front of nitrogen. So 2 and 1. And then I need the molar mass of nitrogen, 2 times 14.01, 28.02. So I get out my calculator, 25.2 divided by 28.02 times 2 times 17.034 equals, and this gives me 30.639 and some other digits. I only get to keep 3 of those though, so that would be 30.6 grams of ammonia. So what's the answer to the question? What maximum amount of ammonia in grams can be made? 30.6. If I had looked at these starting amounts and decided that I didn't need to do the second calculation because this is so much smaller, I would have been wrong. Any questions? I guess this one is a little different. It's like, man, another one. I don't look at these slides before I come to lecture because it's more exciting that way for me. So I never know what's coming up next. Okay, so this is similar, but it is different, so we're going to go ahead and do it. This reaction is used to obtain iron from iron ore. There it is. The reaction of 185 grams of Fe2O3 with 95.3 grams of CO produces 87.4 grams of Fe. Find the limiting reactant, theoretical yield, and percent yield. Okay, the first thing is you got to read through the whole problem because it could be like some trick question and it could ask you what color the sky is at the end and then you wouldn't have to do anything else. Unfortunately, that's not going to happen on an exam. So after I read through, I'm going to find the numbers and I'm going to write them down. So 185 grams of Fe2O3. Okay, so 185 grams. And 95.3 grams of CO. And 87.4 grams of iron. And it wants limiting reactant, theoretical yield. Okay, we've been doing those sorts of problems. And it also wants the percent yield. What's different about this problem compared to the last one? They gave us 3 masses. Why did they give us a mass of product if we're supposed to calculate the mass of product? This is the actual yield. it says that when they react this much of the two reactants, it produces this much. It's not a theoretical yield, that's the actual yield. The actual yield will always be given to you in a problem. So this is the actual yield. So we've been doing theoretical yield. Theoretical yield, we have to do two calculations. We have to take this one and find the mass of iron, and we have to take this one and find the mass of iron, and we pick the smaller, and that's our theoretical yield. How do we find the percent yield? The actual over the theoretical times 100. So the percent yield equals the actual yield over the theoretical yield times 100%. So we are going to use this number, but that's the actual yield. Okay, again with the two calculations. 185 grams of Fe2O3. And I need to go to moles. Moles of Fe2O3, and then moles of product, which this time is iron, and then grams of iron. So here I'm going to have moles, no, not moles, grams. Grams of Fe2O3 in the denominator, because I want these to cancel out. And I'm going to have moles of Fe2O3 down here. So those cancel out. And moles of Fe down here. This middle term, look up here. I've got Fe2O3 in the denominator. There's an implied 1. So I'm going to write 1 in front of moles of Fe2O3. In the numerator, I need moles of iron. I look over here, there's a 2, so that's 2 moles of iron. This time, this last one is easy. Just look at the periodic table, 55.85. It's the molar mass of iron. But then I need the molar mass of Fe2O3. I'm going to have to calculate that. You really should write that down. 2 times 55.85 plus 3 times 16 so 2 times 55.85 plus 3 times 16, 159.7. 1 mole weighs 159.7 grams. So now I've got 185 divided by 159.7 times 2 times 55.85 . 129.3957, blah, blah, blah. Again, our starting number gives us 3 significant figures. So that would be 129 grams of iron. Then I have to take the mass of CO and calculate how much could be made from that. Grams of CO down here. I think this classroom should have revolving doors. I think that'd be great. Moles of Fe, moles of CO. Up here, grams of Fe and moles of Fe. The last term is the same, 55.85. Middle term, we're going to go up here, 3 in front of CO, 2 in front of iron, 3 in front of CO, 2 in front of iron. Need to calculate the molar mass of carbon monoxide, the mass of carbon plus the mass of oxygen, 28.01. So I take my 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals 126.681 and some other digits. That would round to 127 grams of iron. So what's my theoretical yield? 127 grams of iron. What's the limiting reactant? Carbon monoxide. Whoops. Limiting reactant. I still need to calculate the percent yield. So my percent yield trying to dot my I's, is actual over theoretical. So this is our theoretical yield, and this is our actual yield. So 87.4 grams on the top. It's better to use extra digits, the 126.681 in this calculation, instead of rounding it to avoid rounding errors. 126.681 grams, that only has 3 sig figs, times 100%, 87.4 divided by 126.681 times 100. This answer should have 3 significant figures. I'm getting 68.99 219, and if I keep 3, this 9 causes me to round this 9 up, so that's going to be a 0, and the 8's going to round up to a 9. I'm going to get 69.0 as my percent yield. So that's my percent yield, and this is my theoretical yield. The question asks for 3 different answers. Any questions? Stunned silence. This is not on the exam that's on Thursday. It will be on the next exam. But there will be questions like, here's an equation, how much iron could you make from 195 grams of iron? Fe2O3, without the limiting reactant part. So you do need to know the grams to moles to moles to grams part for the exam on Thursday.